So yeah, so far we've seen, I think, a lot of different things like the user interface, building networks, attributes, groups. I mean, everyone here having TouchDesigner knowledge, like building networks everyone is very familiar with that. So in order to, I think, tie everything that we've just seen, tie everything together, we can go through a bunch of different examples of like actually building something from scratch. We'll start with one which is sort of fake fur, and it introduces also another concept, which is volumes, but in a very simple way. And it will make more sense because it's actually like we get a visual result at the end. It makes more sense to just boxes intersecting cubes or spheres. So I'm still working the sim file, but you can either follow along because it's the one called fur.hip, or I'm going to rebuild it from scratch anyway. But so there again, in my root level, my object context, make a geo node and dive in and start building a network for that. So the way we're going to build this is we're going to start from a grid again. And that grid is going to be the base for a volume. And basically a volume is just like, it's voxels to make it like super simple. So it's a box filled with a lot of tiny boxes for those that are not familiar with voxels. And each box can hold a value, say like a vector or a scalar or a matrix, for example. In our case, we're going to build a simple volume, which is just a box. And each of the voxels in this volume holds a vector, which gives you a direction. So essentially, it's just a noise field or like a 3D noise. And we use that to direct a bunch of curves. So, okay, maybe it makes no sense at this point, but we'll see it as we go. So again, create a grid. I always reduce them because it's like the size of 10/10 is big. So we have a grid here. From that, we want to build the volume. So like the simplest way of doing it is to drop down a bound node here, which gives you the bounding box of your geometry. In this case, it's flat. So if we highlight the bounding box, we get just basically a flat bounding box. We want a volume. So in the upper padding here, in the bounding box, if we go to the parameters, we have lower padding, upper padding. If we pad by 1, for example, it gives us like 1 extra unit on top and creates a volume, or like not a volume per se, like in the voxel sense, but in a sort of a geometry with volume. Then, speaking of volumes, we drop down a volume node. And this is basically going to create a voxel, like a bunch of voxels for us. It has an input. If we use this input, the volume is by default going to take the same size as the volume, as the bounds I've just given it. So if we highlight the volume node here, so the rank here is basically what we're storing in each one of the voxels. Is it a scalar, a vector, or a matrix? In our case, we need a vector because we need to store like a direction vector. And we call that, you give it a name so that you can reference it later. And basically just call that vel. So what this means is each one of the voxels is going to have a value called velocity in which we're going to, add a vector. You give it a name because you need to be able to reference it at some other point. If we highlight the volume node here and click the information button, we go down here, we can see that we've got the name we just typed in here. So vel for velocity, so velocity x, y, and z, which corresponds to the rank we have here because it's a vector, so x, y, z. If you go further down in the parameters, we have the uniform sampling. So this is where you're going to basically give the resolution of your volume. that's the number of divisions. So at this point we have like, because it's a 3D, it's like X, Y, Z, we're going to have like 10 by 10 by 10. Or 10 by 5 by 10. Why? Oh, yes. Okay, sorry. So the grid is not the right size. So if we make a grid that's 1 by 1, and then in the bounds we added 1, we've just basically created a box. And then if we go back to the volume and check the information, we have 10 by 10 by 10, X, Y, Z, and each of the X, Y, Z have a value of 1. And there's 10, basically 10 voxels along each axis. At this point, there's nothing in our volume. We can't even see it. If we, for example, go back to the top of the volume parameters where we had like rank, name, and then initial value, everything is at 0 by default. If you add 1, you're basically adding 1 to the X, what's it called? X component of each vector that's stored in the voxel. We'll leave it as 0 because that's not what we want. So in Houdini, you can add a lot of, you can script with Vex or Python, but there's also like a visual, like node language, or like the equivalent of the scripting language. There's also like nodes for it, and they're called VOPs. So if we type volume VOP, and connect the first network to the volume we had highlighted. This, what it does is it allows us to run essentially another network on each one of the components of the volume. So each one of the voxels that we have, we can run, this volume VOP is going to run on it. You could have, you can run Vex on them as well, which is the scripting language. So you could have, if we go to, if you type WR for Rango, you would have like the volume Rango, which lets you run a script on each one of the voxels. It's a bit the same if you're thinking in terms of GLSL, for example, like a pixel shader. You can, the GLSL shader will run one time for each pixel. In this case, if volume Rango is a small piece of code which will run each time for every voxel in your volume. We'll just do it with VOPs because it's a bit quicker to get up and running. So basically, this volume VOP is going to let us create a smaller network, which is going to run for each one of the voxels. So if we dive in to the volume VOP, we have this here, which has got a bunch of parameters which corresponds to parameters from the volume. You get the density for each one of the voxels, the position, and a bunch of other things that is a bit out of the scope at this point. So what we want to build here is pretty much like the cover picture for this workshop. So we want to create a 3D noise field so that then we can bend the curves with a noise. So we would use a curl noise here. So if you type curl noise, drop down a curl noise node, and then we need to get the position of each one of the voxels and use that as the input for the noise. So what it does here is it runs over each one of the voxels in our volume and feeds that position into the noise. And what we want is to take that noise value, which is a 3D vector, and store it inside of the voxels, so that then later on we can read that vector and direct the curve. So if we go back up to where we were earlier on, if you remember, we named this what do you call it? The voxels have a parameter or an attribute, sorry, called vel for velocity. So if we go back into the noise VOP, or like the volume VOP, sorry, and we type bind export, what this node does, the bind export, is it sort of writes back into the voxels the value that we want. So we connect the noise to the input here, and then select the bind export, and we have the name again. So the name that we rewrote was vel. and it's you have to select the type here. It's a vector. So what this has done is it's just basically runs a curl noise for each one of the voxels, and it uses the position as the seed for the noise. And then the bind export takes the value of the noise and stores it into the voxel itself. And that's why earlier on we named the attribute. And then yeah, so if you go back up and you follow along, you should have this here, which is basically a volume which has a noise on it. So each one of the voxels has a different value to it. If you go back to the volume, and we saw this at the bottom, is like the number of divisions we have across each one of the axes. You can, increase this. Be careful when increasing those super high, because volumes tend to take a lot of memory. So you can slow down your computer with this. But yeah, basically it just gives you like the resolution of your volume. So higher resolution means more voxels, means more memory, but also depending on what you're looking for, like nicer results. Yeah, so far we've built a volume that has a bunch of voxels, and each of those voxels has a different vector with a different direction, which is exactly like, if you're building the 3D noises in TouchDesigner with those 3D textures, or even if you're making noise with just a top, you get like just a texture of noise values in there. And for example, if you're doing particles or any other thing, each one of them, each pixel on your top sort of gives you a direction or an orientation. This is the same thing, but in 3D. So we need at this point to create a bunch of curves that are then going to go through the volume. And what happens is just basically your curve goes through the volume and it checks at which voxel it is in that volume, and it orients itself in that direction. And then, you repeat the process, then you get the direction from the next voxel and you turn. It's like basically a flow field. If you're familiar with that, it's like really the same thing. You just orient yourself based on the voxel you've just read and proceed to the next. So we need to build a bunch of curves for that. The easiest thing is if we drop a scatter node, highlight this, and we connect it to the grid. So we're using the initial grid that we started with here, from which we built the volume. We're also using that to scatter just a bunch of points on them. And then Houdini made this extremely simple. You go add a new node called volume trail. Just drop this one here. And what this does is it takes in, the first input is a bunch of points from which it's going to create some trails. And the second one is the velocity volumes, which is exactly what we created here. We created a volume with our noise field in it. So if we connect the points here to the volume trail and then connect the velocity field that we created and highlight it, there we have it. We've just created super simple volume trails. You can then, for example, if you select the volume trails, go to the parameters, there's a trail length. You can just make those longer, shorter. One thing to note is that the way it works is basically it starts with the points here. And each one of those points gets the voxel to which it belongs. So it basically looks at its own position, and it takes the value from the closest voxel in our volume. And then it moves by that value. So that's why we stored the vectors in there, because every time it sort of moves by the value of that vector, and so on. It keeps repeating that. When it eventually at some point leaves the volume, then that's it. The trail is cut. That's why a lot of them that are pointing down the way, when they eventually, negative values, they're going down the way, they eventually leave the volume. To visualize this a bit better, if we go back to the volume VOP and drop a constant, we need to change this to a vector, because there again, we're using 3D vectors in each one of our voxels. And for example, in the vector default, just leave 0, 1, 0. We just created a vector which is pointing up. So 0 on the x-axis, 1 on the y-axis, 0 on the z, so up the way. And if we connect this to the bind export, which basically takes those values and stores them in the voxels, we get this result. For each one of the points that we had here that we scattered from the grid, it reads the value to the closest voxel to that point, and it always has the same vector of like basically like 0, 1, 0. So it goes up by one unit, and then it does again and again and again. And you basically just get like every trail going in the same direction upwards. If we go back to the volume VOP again and then replace, bring back our curl noise back into there, we actually get the result we had before, which is instead of just going up the way, it reads the vector and it orients itself in that direction. To make this a bit more interesting, if you select the noise node here, and you have a mouse with the middle button, if you middle mouse on those, on the input, on the sort of the dot next to the name here, where you would connect the wires, if you click on them, you have this promote parameter. If you click that, what it does is it takes that parameter and it promotes it to the upper level of where you put your node. If that makes no sense, we'll see it in a second. Just if you click that, say type, which is going to be the noise type, frequency, offset is useful, amplitude, for example. So we've promoted all those. If we go back up one level to where we actually started building this network, and you click on the volume VOP, you see that those parameters have just been added here. We have the noise type, the frequency, offset, and amplitude, which correspond to those 4 parameters that we exported, so to speak. It just basically means that you can change those here without having to go back into your VOP and then come back and then go back. You can just basically change them from from up here, which is just basically more convenient. Okay, so then you can basically just use that to start changing the noise parameters, offsets. It's just quicker than diving back in and back out. Lower the amplitude, which is not doing much, but and there we have it. You have sort of a fake fur. If we go back to the scatter node and say 10,000 scattered 10,000 points. Okay, sorry. We have the grid and the scatter node here. I may have gone over this quickly. There's a force total count there, which is basically the number of points that we're scattering. If you decrease this, get less points, increase, get more points. If we increase this number here and then go back to the volume trail, we basically get something that's much more dense and has a lot more trails. The colors are from the volume trail. If you click the volume trail, it has this visualized velocity, which basically visualizes the values that are in the voxels. If you disable them, you get this. It's a bit harder to see because we have no lights in our scene. So I mean, you can keep it on, and it's a bit easier to see what's going on with your noise. Okay, so another thing, to go back to this thing we saw earlier, which was the attributes, where as in like each point, vertex, or primitive can have different values stored on it. We can create an attribute to change the length of the trail. So far, they all have the same length. Some of them look shorter because they exit the volume earlier because of the orientation. As I said earlier, I mean, if your trail sort of leaves the volume by, because it's being directed out of the volume from the vector because of the vectors, that's it. It doesn't update it anymore. Yeah, so if we drop a point wrangle like this and add it here between the scatter and the volume trail, I'm introducing something new here, which is like scripting. It's going to be like super simple, one line of code, so no worries. But just the same way as that in TouchDesigner, we have the script nodes. Like I think like basically you can write Python, which just I don't use it that much, but basically it just lets you manipulate some data. Houdini has the same thing with something called Vex, which is just their own language. You can also use Python, but Vex works specifically on the geometry. So from a Vex node, which is just what we've added here, like a point wrangle, we can start manipulating either attributes or positions or basically like anything related to the geometry that we're working with. So if we go to the volume trail and we had the trail length, which we changed here, and you just hover over the trail length, it says parameter trail len, and that's a parameter that we can, that's an attribute that we can modify here in the wrangle. So if we go back to the scatter, we've scattered a bunch of points, and by default, they don't have a trail len attribute. So the volume trail will basically just pick up this one, the one that we're dialing in here. If here we type f trail len, because it's a float value, basically it's just like a one-dimensional float of the length of the trail, is equal to 1. You don't need to put the 0.0f, it's just a bad habit I have from shaders, but basically that just means that every point here that we've created has a trail length of 1. If we go back to the volume trail and highlight it, nothing has changed because we basically had like very close value. If we go back here to the wrangle and we say, for example, 0.5, we've just made them all shorter. And that's just through this concept of attributes. If we select the wrangle and go back to the geometry sheet, all of the points have a trail length attribute of 0.5. So they all have a length of 0.5. If we wanted to make it, a bit more random, there's a function called rand, which gives you a random number, and it takes a random seed, or it needs a seed. In this case, if you type ptnum is basically like a built-in value which corresponds to the number of the point. So we created a scatter node here, which scattered a bunch of points on there. Each of those points has a unique ID. So from 0 to however many ever points we have. In this case, 11,000. In the wrangle, rand is going to give us, like this ptnum here basically gives you the number of the point that you're executing this code on, because the wrangle is going to happen once for every single point. As you see here, it has like a run over details, primitives, points, vertices, numbers. If you select points, it takes the geometry and it executes this piece of code for each one of the points. So when we had this, it just selects, it just runs over every point in our point cloud here, and it gives it an attribute with a value of 1. If we then randomize that using ptnum, so basically the index or the number of that point, it's going to give you back a different value for each point. And then if we go back to the geo spreadsheet, we see now we still have the trail length attribute, but they all have a completely different value. If on the other hand, we did just ptnum here, So we're still creating an attribute called trail length, but instead of creating a random value, we're just storing the point of that number itself. And we go back here, then you see that, 0, 1, 2, 3, and so on. It just takes the number of the point it's executing the code on and stores it back in that attribute. So what we want is just basically a random value. So each point in this scattered points here is going to get its own different trail length based on this random function here. And if we go back to the volume trail, then I have completely random lengths. There again, I mean, you could, if you go back to the point wrangle and multiply this by 0.1, so make it much shorter, we get a much shorter trail length for each one of the points. I'll leave 25, something like that. And there, I mean, there is just a matter of, just playing with offsets and values and seeing what patterns start looking interesting or not. You can increase the noise frequency. This is, there again, like very similar to anything that you have in TouchDesigner when you're working with a noise top. You have different types of noise, different frequencies, or period, as they call it in TouchDesigner. It's really all the same thing. You can just start like art directing your effects. And if we up this, say like 20,000 points, then you get this pretty dense fake fur. And one other thing to note is that if we highlight the points, and for example, we get closer here, you can realize that if you look up close, like every curve we have is pretty low resolution. You can see that those sort of sharp edges. Houdini has a resample node, which takes those curves and it's just going to resample them. So basically, it's going to take the same curve and just add more points based on a parameter that we set. So if we connect it and highlight it, we've actually get less points here by default. But here, if we go to the parameters, we have a length. Basically, that's this separation between the different points. So if you go and start lowering that value, you start adding more and more points to your curve and getting something a lot more dense, but with a lot more, more definition. You can even lower that a bit more, for example. And if you go further down, there's another parameter called treat polygon as. So you can either treat them as straight edges, and it's just going to keep this sort of, sharp angle we have that is not that pleasing to the eye. And if you select, for example, subdivision curves, it's going to create more of a curve shape from what we had. So we've just gone from this being pretty sharp, resampled it, and we have something that's a lot cleaner, a lot smoother. So this is like a very short example, but they're again building something more concrete and making use of a pretty simple example of attributes. When we scattered the points, they were just different positions in space, and we added on the trail length attribute, which is basically creates. Sorry, I went over this pretty quick. So this means float, and the @ symbol there is just the syntax for an attribute. So that's just the way you define an attribute in this Houdini coding language. So there we have a wrangle that runs over every point in the geometry. So each one of the points that we have in the viewport, for each one of them, it creates a float attribute of name trail length and gives it a random value. That there again, you can see that in the geo spreadsheet. Again, super useful to get all your information. And the volume trail reads that and basically replaces the attribute we have created here. It replaces this one. And we have different trails of different lengths. And then resample them, and you have this thing that's pretty smooth. So, I mean, this is a bit off topic, but if you wanted to start rendering those, these are just curves depending on your rendering engine. You would have to start make building geometry from them. I'm going to lower the number before I do this. I'm going to lower the number of them because I don't want my computer to crash. So I've just gone back to the scatter node and I've lowered the number of trails that we're creating, and they're still resampled the same as before. Pretty smooth. There's a pretty useful node called sweep, which basically takes a curve and sweeps a piece of geometry along it. There's the same one in TouchDesigner, but it's a bit older and it doesn't work exactly the same. So if we drop a sweep node and we select, there's a lot of different parameters in here. The very basic one is the surface shape, and we select, for example, round tube. It's going to sweep cylinder across each one of the trails that we have. If we connect that to the resample node and highlight it, you get this thing. All those cylinders, you just have to lower the radius here, and we've just basically created a bunch of cylinders on top of each one of the spheres trails we had. There again, the number of columns is basically the definition. You can either like have something super low, like ribbon like, because only 2 of them, or triangles, and the higher you go, the smoother they get, but the more geometry you get, and then it starts slowing down a bit. If you toggle wireframe, then you get a different view of it. So there again, just basically built a bunch of, it doesn't look like fur anymore. It looks like something different, but super simple way of using volumes here. Create the bound of your volumes, create the volume itself, add some values to it, some wireframe, and then direct some trails through it. All right, so they don't like, I've just noticed that my volume is much higher. The trails don't go that high because they're super short. If we go back to this and multiply by 5, for example, then we get something that's actually the trails that are going all the way up to the volume. Yeah, so super simple example, but makes more sense than just stacking boxes and spheres together, and makes use of attributes. I don't know if anyone has any questions, or if not, I guess we can move on to building another one a bit more interesting than this.
Dominique, there is a question on a comment.
Yep.
BWXYZ say, it seems to me that software can simulate natural phenomena, but can it reproduce complex things like half mirrors, prisms, and iridescent structure curve? I cannot pronounce this.
Yeah, it can. The thing is, that would be like a rendering topic. You would basically make your, if you talk about a prism, for example, if you make any sort of shape like a prism shape, it's pretty simple. You would just mix a geometry, and then you would have to do that in rendering. So add some caustics or some photons to it. So it's a bit off topic because here we're just looking at like the geometry nodes, but it's when you're rendering, like a lot of renderers nowadays, like can have like iridescence, caustics, photon mapping and all that. So it does, you just have to, it's just more of a rendering thing than a geometry thing.
Okay, thank you.
Welcome. Yeah, so I guess we can move on to building something else, unless, as I say, if anyone has any questions, just ask. What could we build? Okay, so I'm going to go back down one level, hide this, create another geo node, dive into that, and we'll build another example here, which is a bit more complex and introduces there again a bit more some different concepts, but also builds up on some previous ones. So what we're going to build is basically I can't remember what the effect is called, differential lane growth or something. Basically a lane that grows but never intersects, and it creates this pretty cool pattern. So what we need is a curve with some points on it, and then we need a way of adding more points and keeping those points apart. And every time we reiterate and repeat that over time, we get more points sampled onto that curve, exactly like we just saw here with the resample, where we're just adding more points on the curve and giving it more definition. In this example, we're going to use the same concept of taking a curve and adding more points onto it and relaxing those points away from each other, and then reiterate over and over. And the more you add, the more you relax, you start to get this pattern that starts growing, and it looks pretty nice. So we'll start with a circle. This is a bunch of polygons in a circle. What we want is to not have the geometry of it. We want just like the curve around the circle. So we will use closed or open arc, I guess. If you select the arc type here, it's exactly the same as TouchDesigner. Instead of being a closed circle, we start just getting the arc around the circle. And there, if you highlight the points, you see all the points around the circle. So just let me check something. So what we need is something that repeats over time. For that, we're going to use a solver, which is something I wish existed in TouchDesigner. And it's just basically a way of saying that at every frame, we re-enter the solver and we re-execute what's in the solver. A bit in the same way that the VOP we created earlier to create the noise field onto each one of the voxels. There we're not creating it on each one of the points, but we're creating at each iteration or each frame, we re-execute the same thing. So it's sort of like a sort of frame loop. So if we go into the solver, we get a bunch of things. We get prev frame here, and that we get this 4 nodes here, input 1 up to input 4. If we go back out, these correspond to input 1, 2, 3, and 4, corresponds to those 4 inputs we have into the solver here. In our case, we're not going to use that yet. We're just going to use a previous frame. So what it does is every time the solver runs, so at each frame of the animation, we get the previous frame from this node. We run some operations on that, and then it basically gets restored and re-enters as a previous frame at the next frame. So if you start resampling a curve, every time you run, every frame it runs, you're going to resample the curve that you just previously resampled, which is exactly the way that we're going to get this effect working. So the basic concept of this differential lane growth is to get points that are never intersecting each other. They're always a bit pushed apart. You do that in Houdini with the point relaxed. If we drop that and we take the input from the previous frame. So in this case, we start off by just having a circle, and we want to relax all of these points. Back to 3D space. And once we've relaxed it, we want to resample and add more points onto this curve. And then we're going to go back in at the next frame and relax again and add more points. And every time we add more points, these points are going to get relaxed and pushed apart. So we have an error or like a warning here. If you hit this button here for the info panel, it says invalid radius attribute. What the relax needs is something called the p-scale. We saw it earlier at one point when we were instancing spheres, that if you have a p-scale attribute, then every sphere, and you randomize that p-scale attribute, every sphere had a random scale. The way we are going to do this here is with, if we use an attribute create, which we saw earlier, it just lets us create an attribute that then is going to get stored on the geometry. So connect this between the sphere and the solver. By default, it's looking for, if we go back into the solver, onto the relax, it's looking for p-scale. It says point radius attribute, and it's looking for p-scale. So we'll just go back to the attribute create here, call it p-scale because that's what it wants. And it's a point attribute, it's a float type, it's a size of 1, and we will give it a value of, say, 0.02, something quite small. Go back into the solver and the error is gone, or the warning is gone, because we've actually given it here. If we go back to the geo spreadsheet, we've given it a p-scale attribute. They all have the same one. Each point in the geometry has the same value. And when we go into the solver, there again, if we click, select the relax node, each one of the points from the circle that we created has the same p-scale attribute. And then we resample. If we go back up one level and run this simulation, nothing happens. And this is where we have to start figuring out the size for the p-scale attribute, because if they're basically the p-scale that we're creating here, it gives you the minimum distance, or like the size that each point has. So if 2 points are smaller, are closer than that value we've created here, they would get relaxed and get pushed apart. So the smaller this value here, the smaller the p-scale attribute, the smaller the point really is. If they all have really small values, then the algorithm will consider that they're not overlapping. So all I've done here is in the p-scale attribute, I've increased this. We had 0.2, I've increased it to 0.5. Oh, sorry, 0.5, which makes that every one of the points on our circle has a bit of a bigger value, is like a bigger point, so to speak. And then when the relax runs, it's going to take the distance between each of the points and factor in the p-scale attribute and realize, okay, well, these points are closer than their p-scale, so we have to push them away. If you just run the simulation, there again, up key on your up arrow on the keyboard, we start to get this result where things are being pushed apart. There again, what happens is we created the circle with the points on it. Each one of the points is given the p-scale attribute, which is 0.05 for each point. We've added a solver, which is going to repeat basically these nodes at each frame. It takes the previous state and feeds it back in and re-executes those nodes on that, and then so on and so forth. So it takes the points on our circle, it relaxes them, and it resamples the circle. And what happens is when we, as we saw earlier, when we resample, is you're adding more and more dots. The more dots you add, those points are actually getting closer to each other. So when we run again the previous frame, when the solver runs again, it has to relax those points because we added more points on and they're too close. So the relax pushes them away. And it does this at every frame. So at every frame, it starts adding points if you scrub like frame by frame, it starts adding points and pushing them away from each other to satisfy the constraints, you know, this like the relaxed distance. So that's like the super basic version of this. So let's try and make this a bit better. The first thing is that there again, I mean, if you highlight the points by clicking on the point thing here, there again, so we see that the curves don't have that many points, and we really get those sharp angles again. There again, we can solve this by dropping another resample after the solver. And this one is not going to get executed every frame. I mean, it does, but not, you know, in the same way as the solver. The solver is really the one that anything that you put in here takes previous frame, executes the nodes on it, and then restores it to re-come in. It's like a sort of what you call it, it's recursive. This is just at the end of the node chain and it's or the network, and it just resamples our curve. So just like we had on the previous example with the fur, if we go back to the parameters for the resample and we say, for example, lower the length here, you start get a lot more points. And just the same as we did earlier, treat the polygons as straight edges by default or subdivision curves, and we start to get this, you know, much more aesthetically pleasing curves here. All right, so there again, we run this again. It's starting to look a bit better. We've gotten rid of the sharp edges. There's a bunch of stuff we can start playing with. Let's see if we randomize the p scale here, because in this setup so far, each one of the points on the curve has the same p scale. So they have the same, basically the same size, and if they intersect with each other, the relax pushes them apart. So if we drop a attribute randomize, by default, it always works on the color. So we get attribute randomize, and instead of having CD, we work on p scale. It's one dimension because we're just using one float. And we'll say that the minimum value should be 0.04 and maximum value 0.06, for example. There again, like I initialized this to 0.05 and it seemed to work well. So we can, you know, we can set some points a bit smaller and some points a bit bigger. And then if you re-highlight the solver and then rerun it, it's okay, it's not that different. So maybe we have to increase the values here. I don't know, 0.9. Okay, sorry. So reset the whole thing. In the attribute randomize, what we're doing here is we're taking that p-scale value, which was set to 0.05 for every point, and we're randomizing between 0.02 and 0.09. So each point is going to have a random value between those two. So some are going to be smaller, some are going to be bigger. And then again, if we just sort of slowly go through the simulation, we start to get a bit more interesting patterns. It doesn't grow exactly the same way. Some points are going to be closer, some points are going to be a bit further, because each one of them has a different p scale. Okay, so there again, if we rerun this whole thing, if you go back to the beginning of your timeline, select the resample, and then, you know, start scrubbing along, you know, you start to get this pretty nice growth effect, and you don't get any overlaps or anything, except one here, which I think is the start of my, yeah, it's because my circle starts overlapped. To fix this, we can, if we go back to the circle we created at the very start, we selected an open arc to just keep the arc or the curve that builds, that makes up the circle, and it's basically going like a full revolution. So if we lower this just a bit, for example, like this, these points here won't intersect at the start, and if we rerun the solver, we got rid of that intersection that we had. If you go back to the circle, at the start, they were like a full 360 around. And it gave us this intersection that we have. If we just lower this to make the circle open, I guess. Admittedly, I mean, you could use 359 if you really wanted to be super close. And then go back to the start, reset the solver. Again, like every time you see this is orange in the timeline down here, it means that, it needs to be reset, or that something has changed, therefore the simulation must be rerun. There again, we've just like separated the last points in the circle, and we've gotten rid of that overlap that we had here. If we then select the resample node we have at the end, make it much smoother, much nicer. Cool. And then, so yeah, you start to get those different growths here with different sizes. Some points are closer, some points are further. It's more interesting than the one we had at the very start. We can go a bit further with this. If you go into the solver has two interesting parameters at the top here. It has the points to relax and the influencing points. Points to relax is basically, it would be groups in this case. So going back to the concept of groups, where we can select a bunch of points or primitives or vertices and then apply something to them only. So the point to relax is the groups of which, make up the groups of points that actually we want to actually relax, separate from each other. And the influencing points is another group of points which is going to act as sort of a repeller, or like influence the growth. So we're going to play with that. If we go back here, so go back one level down in our network. If we create a grid, and then let's say, don't highlight it, but just like ghost it. So the box is next to the I one. If you click that one, you sort of keep visualizing the same node, but it shows you, like, it ghosts the other one, it shows it, so you can see both. So our grid, if we select the grid, make it XY plane, so it's lying in the same XY plane as the circle we had. Scatter some points onto it. There again, like, you start to see that there are some nodes that get used quite a lot that are pretty useful. For example, we've used the scatter node, I think, in every example. So we have our circle with the lane growth on it, and we just created a grid, and we're scattering points. So I don't know, lower this number of points to, I don't know, 30 or something in the scatter node. So we have this group of points, or like this bunch of points here that's been scattered. It's not currently doing anything. And here, there again, we're going to create an attribute, and the same one as we created before. So we're going to use the p scale attribute, which again is like the scale of the element, or is the thing you're working with. So in our case, it's points. It's going to be like the size of the point that we want. So instead of using the attribute create here, where we set p scale and set the default values of them, we're going to use the point wrangle, which is just like the code version of that. I tend to use the wrangles much more than the attribute create, just because I find it much quicker to work with. It's just a different way of doing things. You can use either the point wrangle or the attribute create. It's the same thing. Just like as an example for variation, we'll use the wrangle. So as we saw earlier, the what do you call it? The syntax, sorry. The syntax when you create an attribute is to use the at sign and then the name. So in this case, we're using p-scale. Also, it's a float, so we need to use the f at float. This is because like if you had a vector attribute, you would use v at sort of like my vector. Or if you had an integer, you would use I at like my ID, for example. It's just the type of the attribute that you're storing. So in our case, float for the p-scale. And then again, if we're using rand pt_num, something like that. So as we saw earlier, the point wrangle runs for each one of the points. So in our case, like the 30 points we just created scattered on the grid, each one of those points could have a p-scale float attribute created on it. That we can see if we go back to the geo spreadsheet. We have a p-scale. And this, just to be clear, is the grid. It's not the line growth we had. This is just like the grid where we're scattering points on. Okay, so they just all have a random p-scale. And then the way we can bring them in here into the solver, there are different ways, but like the quickest is just to use the second input. So we connect the point wrangle we just created with the grid with a p-scale. We're going to lower that. So if we multiply it by 0.1 or 0.2, just make the scales a bit smaller. If you want to visualize them, for example, because here like, it's pretty abstract, we just have numbers we can't see. Remember, we saw this earlier. So you can create a sphere, copy to points, and we can copy this sphere onto these points. And if we highlight it, we actually visualize the size of the p-scale attribute we just created. So pretty small. We can make this a bit bigger, right? So we're not actually using that. We're just using that as like a visualization. So back to the solver, we just created another grid here, scattered some points onto it, gave them all a different p-scale, which is based on a random number. You know that there again, pt_num corresponds to the ID of the ID of each point that we've just that we're iterating over. And then when we come here, what we want is to grab those points from the second input, which is this node here, because we brought them into the second input of our solver. So the first thing we want to make groups. We want groups that are going to be relaxed and groups that are going to influence to sort of change the growth. So we need a group node for the points that we want to relax, and we need a group node for the points that we want to be influencing the others. Okay, so we're going to grab the points from the previous frame. So there again, we're going back to working on the circle we had. If I go back to the start of the timeline. So we're going to create a group every time that we go back into the solver. We want to grab those points and say that, we're creating a group and these are the points we want to relax. So on a group node here, call it, I don't know, circle PTS, circle points, which means we would store all the points from the circle. It's a point group, and basically we want, oops, sorry. If you hit the star key, that's like the wild card, same as like regular expressions and all that stuff. Again, sorry. The star here just means that we're using every point and we're storing every point. So now we have a group here, which corresponds to each one of the points. As you can see here, they're orange. So if they're orange means they've been selected. So every point on the circle is going to be added to that circle points group, and so on, so forth. Every time we go back into the solver, as usual, we sort of re-execute everything. So we'll feed that here to the relax node. And then here we have another group node, which we're going to use to get the points from the grid that we created here. So call it, for example, grid points. There again, we want all of them. So we just add the star here to say we're taking all of them, and it's a point group. So grid points is going to contain all the points from the grid that we're getting in the second slot of the solver node. And we have to merge those. So we're merging the points from the grid to the points from the circle, and we merge them in the solver. We just put the groups before we merge them together so that we can make the difference. Because when you merge the geometry, it just like throws everything together. And we want in the relax node to be able to say, okay, the points from the circle are going to get relaxed, and the points from the grid are going to be influencing that relaxation. And the way of identifying that, as we saw in the relax node, is we have those groups up here. So we need to make the groups before we blend or like merge the geos together. That way we still have a way of differentiating one from the other. So if we go back to the relax node, right here, the points we want to relax, there again, if you go down here, we've created two groups. The ones we want to relax are the points from the circle. We want those points to be first apart, only on the circle. And in the influencing points, what we want is we want the circle points to influence each other, because you want the circle points to push each other away. So we select circle points, but we also want the grid points to be, influencing that growth, but without moving themselves. So we select both groups. We have the groups from the circle points and the grid points. And those are the points that are going to influence the others. So if we select that and run the simulation again, a few steps, it gets pretty slow. If you let it run a lot, you start getting a lot of points, and it's really slow on my computer. If we go back up here to the solver, I've left those. You could ghost this one here with the copy to points, and that lets you visualize where we have the grid points and their size, and basically it shows you how much they're going to be pushing away the lane growth. So if we go back to the very start of the timeline, and you start going through it, you see this growth happening, in which we have those areas like here, because the points on the circle have different scales, and then we've also brought in the points from the grid to sort of make, perturb that even more, or like, push things away even more. To be honest, it's pretty subtle, so we could go back to the point wrangle, in which we set the P scale for the grid points. So for the, basically the size, you can visualize it by the size of the spheres here. So if we double this, for example, we get bigger spheres, and that means that the points on the grid are going to push apart or repel the circle growth even more. And if we run the simulation again, you start to see that depending on the size of those spheres, we get bigger holes. So if we remove the spheres, unghost them, basically, you start to get this growth which has holes in them, which are basically just the holes that, as we've just seen, correspond to the spheres. So that just lets you like repel things or add a bit more, something more interesting to the simulation. There again, I mean, if we multiply them by 1.5, for example, so we're just making those spheres, again, if you highlight them, we're just making those points on the grid even bigger to repel the simulation even more. And then there again, you start to get interesting details of growth being pushed away partly by the circle points themselves, because we give them random p-scales, and the points on the grid, which are pushing things apart even more. And then if you hit enable the resample, there again, just smoothing out the result of the simulation. There's a few more things we could do with this to make it a bit more interesting still. If we go back into the solver, where once again, this is like where every frame, everything is happening based on the previous frame. So we get the previous frame, we create the group that's made up just only with the points that are actually on the circle. We could add, for example, a point wrangle again, just here added after the group node, where we've created the group with the circle points. We could change here their p-scale. So there again, we get, go back to the start here. Okay, it doesn't look like a circle anymore because it's being relaxed, but these are all the points we had on what was initially a circle. If we, there again, play with the p-scale attribute, just set it to 0 for now. There again, we've seen, check the geo spreadsheet. We have the group because they're on the group, the circle points group, and they all have a p-scale attribute, which I've just set to 0. There's an interesting function. I mean, this is more like a bit of a scripting thing. If you've done Python in TouchDesigner, this is not super hard. There's a function called fit01. And what that does is it takes a number between 0 and 1 and fits it into another range. So if we use what we saw earlier, which is rand of ptnum, there again, it's a function that gives you back a random number. And the seed for that function is the number of the point. Every time this seed is different, the random point, the rand function gives you a different value. So because each one of the points in the geometry is unique from 0 to however many ever points you have, this is always going to give, the rand function here will always give you back a different number. Therefore, we're sure that every point in a geometry has a different value for p-scale. It just adds more, variation to it. Rand gives you back a value between a random value between 0 and 1. And the fit function that we're using here basically says, I'm taking this value between 0 and 1 and remapping it to another range. So if we do something like this, for example, that we have 3 parameters. We have the first number between 0 and 1, and we're remapping it to 0.02 or 0.06. That just means that when rand gives back the value 0, we actually remap that to 0.02. That becomes the lowest number we can get. And if rand returns the number 1, then we remap that to 0.06. It's just basically a remapping function where you can change the range of values that you're getting, because 0 and 1 is going to be a bit too big, a bit too like coarse, and we want something smoother between 0.02 and 0.06 to make it smaller. And so what happens in this case, the only thing we changed really is that every time, so sorry, we started with a circle and we set a p-scale value, which was 0.05, was just a value that we give it, and every one of the point has the same one. We then created the attribute randomize between 0.02 and 0.09, which means that the points that we have on this current circle have random values between those within that range here. But every time that we run this, we resample. Therefore, as we've seen before, resampling is just we add more points along the curve, and then we go back and then we add even more points, and we relax and add more points and so on. All the new points that we add every time we go through like one different frame, they get the default value that we set. So they all get 0.05. So this attribute randomize here is actually not making much difference, because every time we add more points after a resample, they get the same p-scale value. So we don't get much of a, we get a very uniform sort of distribution or relaxation. On the other hand, if we add this, randomization of the p-scale attribute, if we add it here, then we're running that for each time we get back into the solver for each frame. Therefore, if, once we've run the solver and we've added more points from a resample, we get back into the solver and we randomize those points. That's the way we take away their default 0.05 value. And if we run this, we start to get even more interesting results where they push each other away differently. One thing we can do to visualize this better is if I should have done this before. If you right click on this and select disconnect, and then go back to the relax and just clear grid points, like delete grid points from the relax. We're basically just taking away the grid points we made there. It's just to visualize the p-scale thing that we just did. So we're back to the start where we had only the circle influencing itself. If we go back to the beginning of the simulation, we get something a bit different, because we've got this p-scale that, instead of being the same for each point, is basically being randomized at every frame. Maybe we can increase this a bit more, okay, there we go, lots of points. But the growth is very different, because every point at every frame actually has a random. I'm going to put this back to something a bit lower because I'm getting too many points. We get a more interesting growth than when every point has the same value. Whoops, sorry. So there again, we're going back. If you have to reconnect the grid points to the merge node, and then we go back to the relax, and we have to reset grid points. That way, we go back to what we had of having the circle repelling, like relaxing itself, and the grid points also repelling, relaxing the circle points, and we start to get this like even more interesting growth happening, where if we visualize the points on the grid, we start to get this pretty neat growth happening here. Again, I mean, if anyone has any questions, just ask. And then, just select the resample. And to be fair, okay, so we introduced like the notion of a solver, which is, taking the previous frame, running some nodes on it, and then restoring it and doing that at every frame. But it's a pretty small network just to get this pretty neat effect of growth. What more could we do with it? We could Okay, so sometimes Houdini's viewport messes up and keeps. Okay. So we could, at this point, for example, if we add a point wrangle, I guess it's just to see a bit more like the way the wrangles work, which is the same as like the Python operators in TouchDesigner. What can we do with this? Okay, like what if we delete the last points? So yeah, so we get this, start with a circle, we have a number of points on it, and then when we hit the resample here, it adds more points between those points. Just like basically like makes a higher definition curve at each frame. With the point wrangle here, we could say, for example, that each frame we want to delete some of the points from the curve, see what happens. So we could delete, for example, the last X number of points from the curve, I guess. Okay, let me just try this. See if this makes sense. Sort of. Yes, okay, so you can see it there. I'll explain what this does in just one sec. You can see it there when we're progressing through the, you can see the end of the curve here, it gets deleted. So what happens when you're adding points with a resample is you just basically add more points, and those points have an ID, which is, you know, that PT num. So from 0 to, in this case, 0 to 330. What I've done here is I've just said at each frame, if the number of the point is below like the current frame number divided by 6, and I remove that point. It's just to remove like the trailing things. The initial points we have the lower values, so like the lower numbers, so 0, 1, 2, 3, and every time we resample, like the newer points have higher point values or higher point numbers. So I mean, this is just, I just made this up. It's just like at each frame, if the what do you call it, the number of my point is inferior to the frame index divided by 6, whatever that's going to be, then I delete it. So basically at each frame, all the points that are under like that have an ID that's like between or like below 13 divided by 6, 20 divided by 6, and so on get deleted. So I'm just deleting the trail end of my curve. And that's if we actually go back up and run this again, you start to get yet another like take on the growth where, you know, like the trailing end of the curve is always deleted, and it never grows that much, because we're at each frame, we're reducing the number of points on that curve, and it just sort of grows differently instead of just growing bigger and bigger. Yeah, so there again, as I say, like if anyone has any questions, feel free. I would say like this is pretty much the whole effect, like built from scratch. If we just compare that by using the resample only here, like if you don't need to delete the node here at the end. It's going to stop on the one that's currently visible. So the node, the little piece of code here that deletes the trailing end of the curve is not going to be used. And if we run this one again, which was the initial one we had, yeah. So my computer is slowing down here with it, but basically we get this growth that just like expands slowly. And if we use this, go back to resetting the wrangle that deletes the tail end of the curve, we get a different one where instead of just like expanding over time, it sort of shifts. And then very much like at the end, the resample to keep everything smooth. Yeah, I mean, yeah. So you could, for example, if we added normals to this, so if we another point wrangle, so for each point, we want to just like create a normal that's, because we're aligned with the XY plane, so create a normal that's along the Z axis. So there again, it's a vector normal. So we use the normal, it's an attribute. So we're using the attribute syntax of like calling it a vector, the at for the attribute with the name of n for normal, which is like pretty much built in by default. And this is one of the ways of declaring a vector. So we're setting the vector to be 0 on the x-axis, 0 y-axis, and 1 on the z-axis, so along the z-axis of here. And then there's this node called polyextrude, which is going to basically like extrude the geometry. And in this case, we only have like a curve, so it's just going to make the curve, I don't know how to say it, stand up, be extruded, I don't know. Okay. So we're getting this result, which is not what we want, because the extrusion mode here is set to primitive or edge normal. And in our case, in the wrangle here, where we just set for each point a normal going along the z-axis, they all have the same one. We need to select, instead of using the primitive or edge normal, use the point normal. And then if the more you extrude this here, this is just basically the extrusion size, you get this sort of, this shape here. So either at first we had the curve, or if you extrude it, you get more of this, I don't know, ribbon sort of thing. As we did earlier with the fur example, if you were to use a sweep node here and set that to round tube and connect this one, maybe up the radius, well, then instead of having this, either this sort of ribbon effect or just the very flat curves, you could have a, what you call it, like a cylinder. You have to be careful of those, because the bigger the radius is, of course, you start to get intersections. Yeah, so these are just things like, they're again ways of sort of visualizing the growth in different shapes. This one is actually pretty neat. Yeah, and I mean, that's it. That's a very simple example of something that's actually pretty straightforward when you think of it. It's 15 or 20 nodes. There's not that much, and it's like pretty easy to get up and running. Just create a curve, and then, I mean, we added a lot of stuff with the grid and the, deleting the tail end. But if you take the different groups here, but if you take the what we started with was just like a circle and create a p scale for each point, and then basically relax and resample, and very quickly we had something up and running. So yeah, I mean, we're pretty much done with this one. If anyone has any questions, or if it's break time or whatever or not, there's another one we can go over, which is a bit different concepts, but still along the same type of effect. But yeah, I don't.
Hey, Dominic, so maybe we can take some breaks, because I think we do like 1.5 hours. without taking a break. So maybe we can do a 5 minutes break.
Yeah, I mean, if we want to go over, I have like another example, or if it's your call. It's a bit long, so I don't know. I mean, I'm okay for going on with it. There's no problem. It's just if you guys, if we have time for it.
Okay, so then we're gonna take a 5 minutes break, and then we can do last session.
Yeah, I mean, it's built in sort of different steps, so maybe we don't get to the very last step, but it's, I mean, very quickly we have something running, like 3 nodes, and we have particles running. So yeah, we can just, I guess, go through that after the break and see if we have time to go through the whole example or not.
Sure, sounds great. Okay,